Space reveals itself through information. Every photon reaching Earth tonight, every particle recorded by a detector, every radio signal captured by an antenna, arrives after traveling for a finite duration. Each carries a message from a specific distance, emitted at a specific moment in the past. The universe communicates with us gradually, constrained by the speed at which information can move. This physical reality defines the observable universe. Cosmologists use this term to describe a spherical region centered on Earth, bounded by the maximum distance from which light has had time to arrive since the universe became transparent. This boundary arises from time, not structure. It reflects the age of the universe combined with the finite speed of light. The observable universe extends far beyond 13.8 billion light-years. Because space itself expands, light emitted long ago travelled through a universe that stretched as the photons moved. As a result, the matter that released those photons now resides far beyond where it once was. The present radius of the observable universe reaches roughly 46 billion light-years. This boundary does not mark an edge of reality. It marks the reach of causality. Beyond this horizon, space may continue. Matter may exist. Physical processes may unfold. What changes is the ability for information to connect those regions to us. The observable universe represents everything that has had sufficient time to communicate with Earth since the early universe. Light travel time governs this limit. No signal carrying information exceeds the speed of light, setting a universal speed limit for causality. As a result, the universe reveals its history progressively. Observations of the Sun show it as it appeared about 8 minutes ago. Observations of the Andromeda Galaxy reveal it as it existed roughly 2.5 million years ago. Observations of the cosmic microwave background reach back nearly 13.8 billion years, capturing radiation released when the universe was only about 380,000 years old. That ancient radiation defines a surface known as the particle horizon. At earlier times, the universe existed in a hot, dense, ionized state. Photons scattered constantly off charged particles, preventing long-distance travel. As expansion cooled the cosmos, atoms formed and light began moving freely. Those same photons still travel today, stretched into microwave wavelengths by the expansion of space. The observable universe therefore reflects both distance and physical history. Observation depends on when information became capable of travelling, not merely on how far it had to go. This leads to another fundamental constraint. Information itself remains finite within the observable universe. Only a limited amount of matter, energy, and information exists within our cosmic horizon. A finite number of particles can be observed. A finite number of quantum states can be accessed. Even with perfect instruments, fundamental limits restrict what can ever be known from within this region. Cosmology encounters boundaries imposed by causality, thermodynamics, and quantum mechanics, not simply by technology. This distinction separates existence from observation. For much of human history, the visible sky appeared to represent the whole of reality. The Milky Way once seemed to contain everything. Even after astronomers discovered other galaxies, the visible universe still felt complete. Modern cosmology has replaced that intuition with a deeper understanding. General relativity allows space to extend indefinitely. Observations indicate that the universe appears remarkably flat on large scales. Flat geometry permits infinite extension, even if it does not require it. When combined with cosmic inflation, the simplest mathematical descriptions point toward a universe vastly larger than the observable region, possibly infinite in extent. Nothing in the fundamental equations assigns special status to our location. Physical laws appear uniform in every direction. Matter distributes itself statistically evenly when averaged across immense distances. This property, known as cosmic homogeneity and isotropy, suggests that our region does not occupy a privileged position. A universe that looks the same wherever we observe encourages the conclusion that similar conditions continue beyond our horizon. This assumption carries powerful implications. If space extends far beyond what we observe, then every galaxy, star, and planet we see occupies a tiny fraction of the total cosmic volume. The observable universe becomes a region defined by time rather than by structure, a patch illuminated by causal contact. The origin of this idea lies in early universe physics rather than speculation. One early clue emerged from a puzzle known as the horizon problem. Measurements of the cosmic microwave background revealed extraordinary uniformity. Regions of the sky separated by immense distances exhibit nearly identical temperatures, matching to 1 part in 100,000. Under ordinary cosmic expansion, these regions lacked sufficient time to exchange information and reach equilibrium. A mechanism was required to explain this coherence. Cosmic inflation provided that mechanism. Inflation proposes a brief epoch of rapid expansion during the universe's earliest moments. During this phase, a tiny region once in causal contact expanded dramatically, stretching uniform conditions across vast distances. Inflation explains why the universe appears smooth, flat, and structured the way it does. This explanation carries a profound consequence. Inflation implies that the observable universe represents only a small portion of a much larger inflating space. Our cosmic region becomes one outcome of a broader process rather than the entirety of existence. Another hint arises from the expansion of the universe today. Observations show that cosmic expansion accelerates, driven by dark energy. This reveals that empty space possesses physical properties. Vacuum behaves as an active component of the universe rather than an absence. Vacuum energy suggests the possibility of multiple stable states. In quantum field theory, fields commonly settle into different energy configurations. Phase transitions occur throughout physics. Water freezes, magnets align, materials change structure. Fields adopt different arrangements depending on conditions. Cosmic space may follow similar rules. Different regions could settle into different vacuum states, each with its own physical properties. Even before inflationary theory matured, this idea already existed within theoretical physics as a natural consequence of field behavior. At this stage, the multiverse remains a possibility rather than a conclusion. The observable universe emerges as a sample, a data set shaped by time, speed, and physical law. It represents the portion of reality that has had causal contact with us since the universe became transparent. Beyond it may lie more space, more structure, governed by familiar laws or by variations shaped by different conditions. This perspective requires no exotic assumptions yet. Space, time, expansion, and causality alone lead naturally to the idea that our universe may represent one region among many. Before we go deeper, if you enjoy exploring the quiet wonders of the cosmos like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow, and it keeps these journeys alive. Modern cosmology places us at the center of a horizon rather than at the center of existence. That horizon reflects the reach of information, not the boundary of reality. The universe we observe includes everything that has had time to reach us. Once this distinction becomes clear, a larger question emerges naturally. If our universe occupies only one region within a far larger structure, what else exists beyond the limits of our cosmic light cone? A fraction of a second after the universe began expanding, space itself entered an extraordinary phase. During this moment, the universe grew at a pace far beyond anything seen before or since. Distances doubled, then doubled again, not because matter rushed outward, but because space expanded between everything. This brief episode reshaped the cosmos so completely that its fingerprints remain visible billions of years later, etched into the structure of galaxies and the faint radiation filling the sky. This episode is known as cosmic inflation. Inflation emerged from a practical scientific need rather than from speculation about multiple universes. Physicists sought to understand why the universe appears so smooth, so geometrically simple, and so delicately balanced. The answers required a mechanism capable of shaping the early universe with remarkable efficiency. In the late 1970s and early 1980s, cosmology faced several deep puzzles. One concerned geometry. Measurements suggested that space on large scales appeared nearly flat, meaning parallel lines remain parallel and the angles of large triangles add up to 180 degrees. Flatness represents a finely balanced condition. Even a slight deviation in the early universe would have grown dramatically over time, producing a universe that curved strongly inward or outward. Another puzzle concerned uniformity. The early universe appeared almost perfectly homogeneous. Matter and radiation spread themselves evenly across vast distances. This smoothness extended across regions that, under ordinary expansion, could never have exchanged information or energy. A third puzzle involved structure. Galaxies, clusters, and cosmic filaments exist today, yet the early universe began in an extremely smooth state. Small variations had to exist early on, but their origin remained unclear. These problems pointed toward a common solution. In 1980, Alan Guth proposed a radical idea. He suggested that the early universe underwent a phase transition, similar in spirit to processes seen in particle physics. During this transition, a form of energy temporarily dominated the universe, driving exponential expansion. Guth's original motivation centered on particle physics rather than cosmology alone. Certain grand unified theories predicted exotic objects and conditions that failed to appear in observations. Inflation provided a way to dilute these unwanted relics by stretching space so dramatically that any such objects became vanishingly rare within our observable region. As the idea developed, its explanatory power grew. Inflation addressed the flatness problem by stretching space until any initial curvature became negligible. A curved surface expanded enough begins to look flat locally, much like Earth's surface appears flat to someone standing on it. Inflation achieved this effect on a cosmic scale, smoothing geometry across immense distances. Inflation also explained homogeneity. Before inflation, a small region of space existed in close causal contact. Energy, temperature, and physical conditions equilibrated naturally. Inflation then expanded that once uniform region to scales far larger than the observable universe. As a result, regions now separated by billions of light years share nearly identical properties because they originated from the same small connected patch. Structure formation found its explanation through quantum physics. During inflation, microscopic quantum fluctuations existed in all fields, including the field driving inflation itself. Inflation stretched these tiny fluctuations to macroscopic scales. Slight differences in density became frozen into space as inflation ended. Over billions of years, gravity amplified these variations, forming galaxies, clusters, and the cosmic web. In this picture, every galaxy traces its origin to quantum fluctuations smaller than an atomic nucleus. Inflation converted the uncertainty inherent in quantum mechanics into the large-scale structure of the universe. Evidence for inflation appears indirectly through observation. Measurements of the cosmic microwave background reveal temperature fluctuations with statistical properties matching inflationary predictions. The distribution of galaxies reflects the same pattern. Flat geometry remains consistent with precise cosmological surveys. While inflation itself unfolded too early to observe directly, its consequences align strikingly well with data. As inflationary theory matured, physicists explored variations and refinements. These developments revealed a surprising implication. Inflation tends to continue. In many models, inflation occurs when a field known as the inflaton occupies a high-energy state. As long as this state persists, space expands rapidly. Inflation ends locally when the field transitions to a lower energy configuration, releasing energy and reheating space with particles and radiation. This process gives rise to regions like our observable universe. Crucially, this transition does not occur everywhere at once. Quantum fluctuations cause the inflaton field to decay at different times in different locations. While inflation ends in one region, it continues elsewhere. Some regions stop inflating and form universes filled with matter and radiation. Other regions keep expanding exponentially. This process leads to eternal inflation. In eternal inflation, the universe contains an ever-growing inflating background within which countless pockets form. Each pocket arises when inflation ends locally. Each pocket evolves as a separate universe, causally disconnected from others due to the continued expansion of space between them. Our universe fits naturally into this framework. From this perspective, our observable universe formed inside one such pocket. Inflation ended here, reheating space and setting the stage for the hot Big Bang evolution. Elsewhere, inflation continued, generating additional pockets with their own cosmic histories. Multiplicity arises as a consequence rather than an assumption. Once inflation behaves this way, the production of multiple universes becomes unavoidable in many models. The inflating background expands faster than regions can decay, ensuring that inflation never ends globally. The process continues indefinitely, producing an enormous ensemble of universes. Each universe emerges from the same underlying physics, yet local conditions can vary. The precise properties of a universe depend on how inflation ends within that region. The energy released during reheating influences particle production. Fields settle into particular configurations. Physical constants take on specific values. Even the number of spatial dimensions could vary in some theoretical frameworks. This diversity originates from well-understood physical principles, quantum fluctuations, field dynamics, and phase transitions. Inflation therefore shifts the meaning of the universe. Instead of referring to a single connected entity, the term may describe a vast collection of regions sharing a common origin but remaining forever separated by cosmic expansion. Importantly, this idea stretches scientific reasoning without abandoning it. Inflation remains grounded in quantum field theory and general relativity. Eternal inflation follows naturally from the mathematics of certain inflationary potentials. The multiverse emerges not as a philosophical add-on, but as a byproduct of equations already used to explain observable data. Skepticism remains healthy. Not all inflationary models produce eternal inflation. Observational confirmation of the multiverse itself remains elusive. Yet the mechanism linking inflation to multiplicity stands as a robust theoretical insight. The early universe, once imagined as a single explosive beginning, becomes a dynamic landscape. Expansion unfolds unevenly. Regions evolve independently. Our cosmic home appears as one bubble within a far larger inflating expanse. This picture reshapes perspective. The smoothness of the sky, the flatness of space, and the distribution of galaxies no longer describe global properties of existence. They describe the local conditions inside one region where inflation ended in a particular way. As understanding deepens, inflation stops functioning merely as a solution to early universe puzzles. It becomes a generative mechanism capable of producing a vast ensemble of universes through the same physical laws tested within our own. With inflation, multiplicity enters cosmology quietly, mathematically, and almost reluctantly. The universe expands, inflation continues elsewhere, and pockets like ours keep forming within an ever-growing cosmic background. This realization leads naturally to a deeper question, one that follows directly from inflation's success. If inflation generates many universes, how many different kinds of universes can exist, and how different can they be? Very early in cosmic history, space entered a regime governed by extreme energy density. During this phase, expansion occurred at an exponential rate. Distances increased rapidly, not through motion within space, but through the expansion of space itself. This process unfolded over an extremely short interval, yet its consequences determined the large-scale structure of the universe we observe today. This process is known as cosmic inflation. Inflation originated as a solution to concrete problems in cosmology rather than as a proposal about multiple universes. Observations of the universe revealed several features that standard expansion could not easily explain. These features appeared independently, yet they pointed toward a single underlying mechanism. One such feature involved geometry. Measurements of the universe indicate that space appears very close to geometrically flat. On large scales, parallel lines remain parallel, and the total energy density closely matches the critical value separating open and closed geometries. This condition requires remarkable balance in the early universe. Even a small deviation from flatness shortly after the Big Bang would have grown rapidly over time, leading to a universe dominated either by rapid collapse or extreme curvature. Another feature involved uniformity. Observations of the cosmic microwave background reveal nearly identical temperatures across regions separated by vast distances. These regions originated so far apart that ordinary expansion would not allow them to exchange information or energy early in cosmic history, yet they exhibit nearly identical physical conditions. A third feature involved structure. Galaxies, galaxy clusters, and large-scale filaments populate the universe today. These structures grew from tiny initial variations in density. The origin of these variations required explanation, particularly given the extraordinary smoothness of the early universe. In 1980, Alan Guth proposed inflation as a unified explanation for these observations. His work emerged from particle physics, specifically from attempts to understand phase transitions predicted by grand unified theories. These theories suggested conditions that conflicted with observation, including the expected production of exotic relics. Rapid expansion offered a way to dilute such relics to negligible levels within the observable universe. As the concept developed, its cosmological implications became clear. Inflation explains flatness through geometric stretching. When space expands exponentially, any initial curvature becomes diluted. A surface that expands sufficiently appears locally flat, even if it began with curvature. Inflation applied this principle on cosmic scales, producing a universe that appears flat across vast distances. Inflation explains homogeneity through causal contact. Before inflation, a small region of space existed in thermal equilibrium. Physical processes equalized temperature, density, and field configurations within that region. Inflation then expanded this once connected patch to a size far exceeding the observable universe. Regions, now separated by billions of light-years, share nearly identical properties because they originated within that single equilibrated domain. Structure arises naturally through quantum fluctuations. During inflation, quantum mechanics introduced tiny fluctuations in the energy density of fields. These fluctuations existed at microscopic scales. Inflation stretched them to macroscopic sizes, imprinting small variations in density throughout space. When inflation ended, these variations remained frozen into the expanding universe. Over billions of years, gravity amplified these initial differences. Denser regions attracted more matter, forming galaxies and clusters. Less dense regions expanded into cosmic voids. The large-scale structure of the universe traces directly back to quantum fluctuations stretched by inflation. Observational evidence supports this framework. Measurements of the cosmic microwave background show temperature variations with a nearly scale-invariant spectrum matching inflationary predictions. Surveys of galaxy distributions reveal patterns consistent with inflation-generated density fluctuations. Precision measurements continue to confirm near-flat geometry. While inflation itself occurred too early for direct observation, its consequences align closely with empirical data. As physicists explored inflation further, an important property emerged. Inflation depends on the behavior of a scalar field, often called the inflaton. As long as this field remains in a high-energy configuration, space expands rapidly. Inflation ends locally when the field transitions to a lower energy state. This transition releases energy, producing particles and radiation in a process known as reheating. Reheating marks the beginning of a hot, expanding universe like our own. Quantum mechanics introduces variability into this process. Fluctuations cause the inflation field to decay at different times in different regions. Inflation ends in some locations while continuing in others. Regions where inflation ends form expanding universes filled with matter and radiation. Regions where inflation persists continue expanding at an accelerated rate. This behavior leads to eternal inflation. In eternal inflation, the inflating background grows faster than regions can transition out of it. As a result, inflation continues indefinitely in some areas while producing isolated pockets where it ends. Each pocket evolves independently, separated from others by rapidly expanding space. Our observable universe fits naturally into this description. From this perspective, our universe formed inside one such pocket. Inflation ended locally, reheating space and initiating the standard Big Bang evolution. Elsewhere, inflation persisted, producing additional pockets beyond any possible causal contact. Multiplicity emerges directly from the dynamics of inflation. Once inflation behaves in this way, the formation of multiple universes becomes a natural outcome rather than a speculative addition. The underlying physics remains consistent across regions, yet local outcomes vary depending on how inflation ends. The properties of a universe depend on field values, energy release, and symmetry breaking during reheating. Particle types, force strengths, and vacuum states may differ between regions. Some models even allow variation in dimensional structure or physical constants. These differences arise from established physical principles, quantum fluctuations, field dynamics, and phase transitions. Inflation, therefore, reshapes the meaning of the word universe. Instead of describing a single connected entity, it may describe a vast ensemble of regions sharing a common origin yet evolving independently. This framework remains rooted in known physics. General relativity governs expansion, quantum field theory governs fluctuations. Eternal inflation follows mathematically from certain inflationary potentials already used to explain observed data. The multiverse emerges as a consequence of mechanisms developed to solve observational problems, not as an assumption added afterward. Scientific caution remains essential. Various inflationary models exist, and not all lead to eternal inflation. Direct observational access to other universes lies beyond current capabilities. Yet, the logical connection between inflation and multiplicity remains strong within many well-studied models. Inflation transforms cosmology from a single event narrative into a generative process. Expansion proceeds unevenly. Regions exit inflation at different times. Universes form as localized outcomes within a broader inflating background. The smoothness of the sky, the flatness of space, and the distribution of galaxies describe conditions inside one such region. These properties characterize our cosmic neighborhood rather than global reality. As inflation shifts from a solution to a generative mechanism, it quietly opens the door to a larger framework. A framework where our universe represents one realization among many, shaped by the same laws, but expressed through different outcomes. This realization leads directly to a deeper question. If inflation produces many universes, how varied can those universes be, and what determines the laws each one follows? Efforts to unify gravity with quantum mechanics impose severe mathematical constraints on any viable theoretical framework. These constraints eliminate most candidate theories while leaving a small number that remain internally consistent at extremely high energies. Within that narrowed space, however, the surviving theories often admit a surprisingly large number of solutions. This coexistence of rigidity at the level of equations and abundance at the level of outcomes defines a central tension in modern theoretical physics. String theory emerges from this unification effort as a framework capable of incorporating gravity into a quantum description. In string theory, the fundamental objects are one-dimensional strings whose vibrational modes correspond to particles observed at accessible energies. Interactions arise when strings split or join, and gravitational behavior appears naturally through modes that behave like gravitons. These features allow the theory to resolve certain inconsistencies that arise when gravity is treated using conventional quantum field theory. Mathematical consistency requires string theory to exist in more than 4 space-time dimensions. Depending on the formulation, the total number of dimensions reaches 10 or 11, with the additional spatial dimensions compactified to extremely small scales. Rather than extending freely, these extra dimensions form closed geometric structures whose size, shape, and topology influence the physics observed in the extended dimensions. Their presence is not optional, but a consequence of anomaly cancellation and internal consistency. The geometry of the compact dimensions directly determines low-energy physical properties. Allowed vibrational modes of strings depend on geometric features of the compact space, and these modes define particle types, masses, and interaction strengths. Gauge symmetries emerge from geometric symmetries, while coupling constants depend on volumes and curvatures within the extra dimensions. Small geometric differences therefore propagate upward into large differences in observable physics. The equations governing compactification admit many solutions rather than a single preferred one. Even when attention is restricted to a specific class of geometries, such as Calabi-Yau manifolds, the number of distinct shapes grows rapidly as topological features vary. Each distinct geometry supports a different spectrum of physical properties. The solution space expands further when additional stabilizing mechanisms are included. Fluxes provide one such mechanism. In string theory, higher dimensional field strengths can thread through compact dimensions in quantized amounts. These fluxes contribute energy and exert stabilizing forces that prevent the compact dimensions from collapsing or deforming. Different combinations of flux values stabilize different geometries, increasing the number of metastable configurations available to the theory. Each stabilized configuration corresponds to a vacuum state. In this context, a vacuum represents a particular arrangement of fields and geometry that defines the background structure of spacetime. Changing the vacuum changes particle spectra, symmetry breaking patterns, interaction strengths, and vacuum energy. Vacua therefore function as distinct physical environments rather than abstract mathematical curiosities. The number of possible vacuum states increases combinatorially as geometric degrees of freedom and flux choices multiply. Estimates based on known constructions suggest values on the order of 10 to the power of 500 or larger, far exceeding any practical ability to catalogue or enumerate them. Each of these vacua represents a self-consistent solution of the underlying equations. The theory constrains what is allowed, but it allows a vast number of possibilities. In each vacuum, physical constants take values determined by the corresponding configuration. The strength of gravity, the electromagnetic coupling, particle mass ratios, and symmetry structures vary from one vacuum to another. Some configurations support stable atoms and long-lived stars, while others prevent complex structure from forming or lead to rapid cosmic evolution. All of these outcomes arise from the same fundamental equations applied to different solutions. This multiplicity presents a challenge for prediction. Traditional expectations in physics assume that a fundamental theory determines a unique set of constants. Within the landscape framework, the equations determine a space of allowed outcomes rather than a single result. The theory remains predictive in constraining possibilities, but it does not uniquely select one vacuum without additional input. Cosmology supplies a mechanism that connects these mathematical possibilities to physical realization. Inflation operates under conditions where scalar fields explore their potential landscapes, while space-time expands rapidly. Quantum fluctuations influence the local evolution of these fields, causing different regions to follow different trajectories through configuration space. As expansion separates these regions, their differences become frozen into large-scale structure. When inflation ends locally, fields settle into nearby vacuum states. the energy stored in the inflating fields converts into particles and radiation, initiating standard cosmological evolution within that region. Other regions remain in the inflating phase, continuing to expand and later exiting inflation elsewhere. This process distributes different vacuum states across space-time rather than selecting a single one globally. As a result, physical constants vary between regions while remaining fixed within each region after reheating. Differences in compactification geometry and flux stabilization lead directly to differences in observable parameters. Constants appear fundamental within a universe but reflect environmental selection within the broader ensemble produced by inflationary dynamics. Vacuum energy illustrates this mechanism clearly. Different vacuum configurations predict different vacuum energy densities associated with dark energy. Regions with extremely large values expand rapidly, suppressing structure formation, while regions with more moderate values permit gravitational collapse and long-term cosmic evolution. Inflation samples these possibilities without privileging a specific outcome. Extra dimensions remain central throughout this process. Their geometry determines the structure of the vacuum landscape, fluxes stabilize configurations, and inflationary dynamics determine which configurations become realized. Each step follows from established theoretical components rather than narrative interpretation or philosophical overlay. The landscape arises from the internal structure of the theory itself. String theory provides the equations, compactification provides the solution space, and inflation provides the mechanism that populates that space. Physical law remains uniform at the fundamental level, while observed differences arise from which solutions become realized in particular regions. Within this framework, the challenge shifts toward understanding how probabilities are defined across a large ensemble of realizations, and how observations drawn from a single region relate to the broader distribution of possibilities. Addressing that challenge requires confronting issues of measure, typicality, and prediction in a context shaped by extreme multiplicity. Modern physics describes the universe using a small set of dimensionless numbers known as fundamental constants. These constants determine the strengths of forces, the masses of particles, and the rates at which physical processes unfold. Their values remain fixed throughout cosmic history within our observable universe, and they enter every equation governing structure, motion, and interaction. Small numerical differences in these constants lead to large qualitative differences in how a universe behaves. Many of these constants appear to occupy narrow ranges compatible with complex structure. The strength of gravity relative to electromagnetism, the masses of elementary particles, and the coupling constants of the nuclear forces all fall within intervals that permit long-lived stars, stable atoms, and complex chemistry. This observation motivates what is commonly referred to as the fine-tuning problem. Fine-tuning arises from comparison rather than from absolute measurement. A constant acquires significance when its value is varied in theoretical models and the resulting universe is examined. When physicists explore such variations, they find that even modest changes often disrupt key processes. The sensitivity of outcomes to parameter values creates the appearance that the universe sits within a narrow region of a much larger parameter space. Gravity provides a clear example. The gravitational constant sets the strength of attraction between masses. If gravity were significantly stronger relative to other forces, matter in the early universe would collapse rapidly into dense objects. Stars would burn quickly and violently, leaving little time for stable planetary systems to form. If gravity were significantly weaker, matter would struggle to condense at all, preventing the formation of stars and galaxies. Structure formation depends on a balance between gravitational attraction and opposing pressures from radiation and thermal motion. Electromagnetism introduces a different form of sensitivity. The electromagnetic force governs the structure of atoms and the behavior of electrons in chemical bonds. Its strength relative to gravity determines the size of atoms and the energy scales of chemistry. A stronger electromagnetic coupling would tighten atomic bonds and alter reaction rates, potentially suppressing complex molecular structures. A weaker coupling would loosen atomic binding, reducing chemical stability and limiting the range of possible compounds. Nuclear forces impose additional constraints. The strong nuclear force binds protons and neutrons within atomic nuclei. Its precise strength determines which elements can exist and how they form. A slightly weaker strong force would prevent stable nuclei beyond hydrogen, eliminating most of the periodic table. A slightly stronger force would bind nuclei too tightly, suppressing nuclear reactions in stars and altering element formation during stellar evolution. The weak nuclear force influences radioactive decay and stellar processes. Its strength affects how quickly stars burn their fuel and how elements form in supernovae. Changes to the weak interaction modify the balance between protons and neutrons in the early universe, altering the abundance of hydrogen and helium produced during primordial nucleosynthesis. These changes cascade through cosmic history, affecting star formation and chemical complexity. The cosmological constant adds another layer. Vacuum energy influences the rate of cosmic expansion. If its value were much larger, accelerated expansion would dominate early, preventing matter from collapsing into galaxies. If its value were much smaller or negative, gravitational collapse could dominate, leading to a universe that recollapses quickly. Observations indicate a value small enough to permit long-term structure formation, yet large enough to drive late-time acceleration. Taken together, these examples illustrate why the constants appear delicately balanced. Each constant participates in multiple processes simultaneously. Changing one value often affects several physical systems at once. The combined effect restricts the range of values compatible with complex structure far more tightly than any single constraint considered in isolation. This situation invites interpretation. One approach treats fine-tuning as a clue pointing toward deeper laws that uniquely determine the constants. From this perspective, the apparent balance reflects hidden principles not yet discovered. The constants appear fine-tuned because the underlying theory remains incomplete. Another approach interprets fine-tuning through selection rather than necessity. Within a multiverse framework, constants vary across different regions. Universes populate a wide parameter space. Observers arise only in regions where conditions permit complexity, chemistry, and long-lived structures. The observed values then reflect a selection effect rather than a uniquely determined outcome. This line of reasoning is known as anthropic reasoning. Anthropic reasoning does not claim that the universe exists for the sake of observers. Instead, it states that any observation necessarily occurs within a region compatible with the existence of observers. The logic parallels selection effects in other sciences. Observations of Earth's environment reflect conditions compatible with life because life depends on those conditions. Applied to cosmology, anthropic reasoning addresses why observed constants fall within narrow ranges. Universes with incompatible constants remain unobserved because they lack observers. The observed universe appears fine-tuned because only fine-tuned regions permit observation. This reasoning distinguishes between explanation and selection. An explanation derives outcomes from underlying laws. A selection argument explains why certain outcomes are observed among many possibilities. The anthropic approach operates at the level of selection rather than derivation. It accepts the existence of many possible universes and accounts for observed properties by conditioning on the presence of observers. This distinction generates discomfort. Physics traditionally seeks explanations that apply universally and predictively. Selection-based reasoning appears to weaken this goal by accepting multiplicity without unique outcomes. Some physicists view anthropic arguments as a pragmatic response to the landscape of possibilities. Others regard them as a retreat from explanatory depth, The controversy centers on scientific methodology. Anthropic reasoning relies on conditional probabilities rather than direct prediction. It reframes questions from "why must this constant have this value?" to "given that observers exist, what values are likely to be observed?" This shift challenges conventional expectations about what a fundamental theory should provide. Critics argue that anthropic reasoning lacks falsifiability. Because unobserved universes remain inaccessible, claims about their properties resist direct testing. Without independent evidence for the distribution of constants across universes, anthropic arguments risk becoming post hoc explanations rather than predictive tools. Supporters counter that selection effects remain unavoidable in a multiverse context. If inflation and the landscape produce a wide range of physical conditions, ignoring observer selection leads to incorrect expectations. Conditioning on observation becomes necessary rather than optional. The task shifts toward understanding probability distributions across the ensemble rather than predicting unique outcomes. The fine-tuning problem therefore connects directly to the measure problem. To evaluate anthropic arguments quantitatively, one must define how frequently different constants occur across universes. This requires a measure over the space of possible universes. Without such a measure, probabilities remain ambiguous. Different measures lead to different predictions, complicating interpretation. Philosophical discomfort arises alongside technical difficulty. Anthropic reasoning blurs the boundary between physics and philosophy by invoking observers as part of the explanatory framework. Some physicists worry that this introduces subjectivity into a domain traditionally defined by objective laws. Others view it as an inevitable consequence of studying a universe from within. Despite disagreement, fine-tuning remains an empirical observation. The constants possess values that permit complexity. Whether this reflects deep necessity, environmental selection, or a combination of both remains unresolved. Competing interpretations coexist because current theory and observation underdetermine the answer. Within the multiverse framework, fine-tuning loses some of its mystery. Variation across universes transforms delicate balance into statistical rarity rather than coincidence. Observed values occupy a small region of parameter space because that region supports observation. The rarity does not disappear, but its interpretation changes. This shift does not eliminate the need for deeper theory. A complete account still requires understanding why the landscape exists, how inflation samples it, and how probabilities distribute across outcomes. Anthropic reasoning addresses observation within this framework, not its origin. The fine-tuning problem therefore functions as a bridge. It connects fundamental physics, cosmology, probability theory, and philosophy. It forces clarity about what counts as explanation and what role selection plays in interpreting data drawn from a single observable region. As theoretical and observational tools improve, these questions remain open. The constants continue to define the structure of the universe we observe. Their values constrain stars, atoms, chemistry, and time itself. Whether those values reflect necessity, selection, or a deeper principle yet to be discovered remains a central issue in modern cosmology. The multiverse framework does not resolve this issue automatically. It reshapes the question by embedding fine-tuning within a larger space of possibilities. Understanding how prediction operates within that space becomes the next challenge, one that depends on probability, typicality, and the structure of physical law across many possible universes. Quantum mechanics describes physical systems using a mathematical object known as the wave function. The wave function encodes all measurable information about a system, including the probabilities of different outcomes when a measurement is performed. Its evolution in time follows a precise equation that is deterministic and continuous. At this level, the theory does not contain randomness or sudden changes. Superposition lies at the core of this description. A quantum system can occupy a combination of multiple possible states simultaneously. An electron can exist in a superposition of positions, a photon in a superposition of polarizations. an atom in a superposition of energy levels. These superpositions persist as long as the system evolves without interaction that distinguishes between the alternatives. Measurement introduces attention into this picture. In practice, experiments always yield definite outcomes. A detector registers a particle at a specific location. A measuring device records a single value. The standard formulation of quantum mechanics accounts for this by introducing a second rule in addition to the smooth evolution of the wave function. This rule states that upon measurement, the wave function collapses to one of its possible outcomes, with probabilities given by the squared amplitudes of the wave function components. The collapse postulate works operationally but creates conceptual difficulty. The equations governing wave function evolution do not predict collapse. Collapse appears as an additional process that operates only during measurement and lacks a clear physical mechanism. The boundary between quantum systems and classical measuring devices remains undefined within the theory. This difficulty motivated alternative interpretations. One such interpretation was proposed in 1957 by Hugh Everett III while he was a graduate student at Princeton. Everett suggested removing the collapse postulate entirely. In his formulation, the wave function always evolves according to its governing equation, without exception. Measurement does not cause collapse. Instead, it produces a correlation between the measuring device and the system being measured. In this view, the combined system of observer, apparatus, and measured object enters a larger superposition. Each possible outcome becomes associated with a corresponding state of the observer and the apparatus. All outcomes persist within the total wave function, even though each observer experiences only one of them. This process is known as wave function branching. Branching occurs when quantum systems interact in ways that amplify microscopic differences into macroscopic records. A superposed particle interacts with a detector. The detector becomes correlated with the particle's state. The environment rapidly interacts with the detector, spreading information about the outcome across many degrees of freedom. This process, known as decoherence, suppresses interference between different branches of the wave function. Decoherence plays a central role in the many worlds interpretation. It explains why different branches behave independently and why interference between macroscopically distinct outcomes becomes effectively impossible. Each branch evolves as if the others do not exist, even though all remain part of the same underlying wave function. Within this framework, measurement outcomes appear definite because observers become entangled with specific branches. Each observer state corresponds to a particular outcome. From the perspective of an observer inside a branch, the result appears unique and irreversible. The interpretation preserves the mathematical structure of quantum mechanics without modification. The equations governing wave function evolution apply universally. No special role is assigned to measurement. No collapse mechanism is introduced. The theory remains deterministic at the level of the universal wave function, even though individual observers experience probabilistic outcomes. Probability enters through the distribution of amplitudes across branches. The squared amplitude of a branch corresponds to the probability an observer assigns to finding themselves in that branch after a measurement. Deriving this correspondence rigorously remains an area of active research, but many approaches link it to decision theory and rational expectation within branching worlds. The many-worlds interpretation introduces a form of multiplicity distinct from cosmological multiverses. In cosmological models, multiple universes arise from processes such as inflation, vacuum selection, or extra dimensions. These universes occupy different regions of space-time and remain causally disconnected. Each universe follows its own cosmic history, governed by possibly different physical constants. In the many-worlds interpretation, multiplicity arises within a single universal wave function. Branches do not occupy separate regions of space. They coexist within the same mathematical object and share the same physical laws. Branching occurs in Hilbert space rather than in physical space-time. The scale of branching differs as well. Quantum branching occurs continuously and ubiquitously. Every interaction that produces decoherence generates new branches. Branching does not require extreme energy conditions or early universe physics. It occurs during ordinary laboratory measurements, biological processes, and even thermal interactions. This leads to an enormous proliferation of branches over time. Despite this proliferation, branches remain non-interacting after decoherence. The suppression of interference ensures that observers within one branch cannot communicate with or detect other branches. The appearance of a single classical world emerges naturally from this effective isolation. The question of whether quantum branches qualify as real universes depends on how reality is defined. From a formal standpoint, all branches are equally part of the universal wave function. None is mathematically privileged. Each branch contains observers, records, and consistent histories. In that sense, branches function as complete physical worlds. From an experiential standpoint, observers experience only one branch. The others remain inaccessible and undetectable. This resembles the situation in cosmological multiverses, where other universes remain beyond observational reach. The difference lies in ontology rather than observation. Cosmological multiverses posit multiple space-time regions. Many worlds posits multiple histories within a single space-time framework. Both involve unobservable multiplicity inferred from theory rather than direct detection. The many worlds interpretation avoids certain problems at the cost of introducing others. By eliminating collapse, it removes ambiguity about when and how measurement occurs. It treats observers as quantum systems governed by the same laws as everything else. It preserves determinism at the fundamental level. At the same time, it requires accepting the existence of an enormous number of coexisting branches. This challenges intuitions about individuality, identity, and probability. Questions arise about what it means to say that an outcome is likely if all outcomes occur. Within the interpretation, probability refers to self-location within the branching structure. Before a measurement, an observer anticipates becoming correlated with multiple future observer states. The squared amplitudes of branches quantify the relative weights of those future experiences. This framework aligns with how quantum mechanics is used in practice. Physicists calculate probabilities using the wave function and apply them to predict experimental outcomes. The many worlds interpretation retains these calculations unchanged while offering a different account of what the probabilities describe. Experimental tests do not distinguish many worlds from other interpretations directly. All interpretations that reproduce standard quantum mechanics make identical predictions for laboratory experiments. The choice between them depends on conceptual coherence, mathematical simplicity, and compatibility with other theories rather than empirical discrimination. This places many worlds in a similar position to other multiverse ideas. The interpretation emerges from taking the equations seriously and applying them universally. It does not introduce new dynamics or entities beyond those already present in the formalism. The multiplicity follows from the structure of the theory rather than from additional assumptions. The relationship between many worlds and cosmological multiverses remains an open area of discussion. Some approaches treat them as conceptually independent. Quantum branching operates regardless of cosmic structure. Inflationary multiverses arise regardless of quantum interpretation. Other approaches explore possible connections, such as whether quantum branching plays a role in cosmological decoherence during inflation. In both cases, multiplicity enters physics through attempts to maintain consistency and completeness. The many worlds interpretation addresses the measurement problem by removing collapse. Cosmological multiverses address fine-tuning and initial conditions by allowing variation across regions. Each responds to internal pressures within existing theories. The question of reality remains framed by theoretical necessity rather than observation. Branches of the wave function remain inaccessible to each other. Their existence is inferred because removing them would require altering the equations. Accepting them preserves the mathematical structure of quantum mechanics in its simplest form. In this sense, many worlds treats the wave function as the primary physical entity. Classical worlds emerge as approximate descriptions valid within individual branches. The familiar experience of a single outcome reflects the perspective of an observer embedded within one branch of a much larger structure. Quantum mechanics therefore introduces a form of multiplicity that differs in origin and structure from cosmological multiverses, yet shares the feature of extending reality beyond direct observation. Both arise from extending successful theories beyond the limits of everyday intuition. Understanding how these forms of multiplicity relate and whether they reflect different aspects of a deeper underlying framework remains an open question in fundamental physics. Modern physics relies on mathematics not only as a descriptive language, but as the primary tool through which physical reality becomes accessible. Every successful physical theory expresses its laws in mathematical form. Equations define how fields evolve, how particles interact, and how space-time responds to energy and momentum. Over time, this relationship between mathematics and physics has grown tighter, leading some physicists to question whether mathematics merely describes reality or whether it constitutes reality at the most fundamental level. This question becomes especially sharp when physical theories continue to succeed as they grow more abstract. Quantum mechanics relies on complex vector spaces rather than intuitive pictures. General relativity describes gravity through differential geometry rather than forces acting at a distance. In both cases, the mathematical structure carries the explanatory weight, while physical intuition follows afterward. The effectiveness of mathematics in uncovering new physical phenomena suggests a deeper connection than convenience or human invention. One response to this observation treats mathematics as a tool invented to model patterns in nature. Under this view, equations summarize empirical regularities, and their success reflects the adaptability of mathematical systems rather than an ontological claim about existence. Another response treats mathematics as something discovered rather than invented, with structures that exist independently of human minds. In this view, physical reality instantiates particular mathematical structures, and scientific progress consists of identifying which structures correspond to the universe we inhabit. The latter view motivates the idea of mathematical realism. Mathematical realism holds that mathematical objects and relations exist independently of observers, cultures, or physical systems. Numbers, sets, and geometric relations possess objective existence, and physical systems realize subsets of these abstract entities. This philosophical position predates modern physics, but developments in theoretical cosmology and fundamental physics have given it renewed relevance. As physical theories approach deeper levels of abstraction, the distinction between mathematical structure and physical content becomes increasingly difficult to maintain. Quantum fields exist as operators defined on abstract spaces. Space-time itself becomes a geometric object defined by a metric tensor. Particle properties correspond to representations of symmetry groups. At no point does the theory require non-mathematical ingredients beyond initial interpretation. This convergence motivates a more radical proposal. The mathematical universe hypothesis proposes that physical reality is itself a mathematical structure. Under this hypothesis, the universe does not merely obey mathematical laws. It is a mathematical object in the same sense as any well-defined structure studied in mathematics. Physical existence and mathematical existence become equivalent. This idea has been articulated most prominently by Max Tegmark. Tegmark argues that if the external world exists independently of human observers, then its description should not depend on human concepts or language. Mathematics provides a framework that remains invariant across observers and interpretations. If a structure exists mathematically and possesses internal consistency, then it exists physically as well. Within this framework, the distinction between possible and actual universes dissolves. Every mathematically consistent structure exists in the same ontological sense. Our universe corresponds to one such structure, characterized by specific equations, symmetries, and parameters. Other mathematical structures correspond to other universes, whether or not they resemble our own. This proposal reframes the multiverse. Instead of arising from cosmological processes such as inflation or vacuum selection, multiplicity arises from the space of all mathematical structures. Existence becomes coextensive with mathematical consistency. Any structure free of internal contradiction exists as a universe, regardless of whether it supports observers, particles, or space-time as we understand them. To organize this idea, Tegmark introduced a classification scheme known as the levels of multiverse. Each level corresponds to a different sense in which universes can differ, ordered by increasing abstraction. At the first level, the multiverse consists of regions beyond our observable horizon. These regions follow the same physical laws and constants, but remain causally disconnected due to the finite speed of light and cosmic expansion. This level arises naturally from standard cosmology and does not require new physical principles. At the second level, the multiverse consists of regions with different effective physical laws. These differences arise from mechanisms such as eternal inflation and vacuum selection. Constants, particle content, and symmetry-breaking patterns vary between regions, while the underlying theoretical framework remains the same. This level corresponds closely to the landscape discussed earlier. At the third level, the multiverse corresponds to the many worlds interpretation of quantum mechanics. Here, multiplicity arises from wave function branching rather than spatial separation. All possible outcomes of quantum processes persist within a universal wave function, producing parallel branches with shared physical laws but different histories. At the fourth level, the multiverse encompasses all mathematical structures. Physical laws themselves vary between universes, not as parameters within a theory, but as entirely different equations. Some universes resemble ours. Others possess different dimensionality, symmetry, or logical structure. All exist equally by virtue of mathematical consistency. This fourth level represents the most radical extension of the multiverse concept. Within this framework, asking why our universe has its particular laws becomes equivalent to asking why we find ourselves within a particular mathematical structure. The question shifts from necessity to selection. Observers arise only in structures capable of supporting complex information processing. Observation therefore samples a subset of mathematical existence. Mathematical universes do not require space-time, particles, or fields in any familiar sense. A universe may consist of abstract relations without geometry or causality as humans experience it. Our physical intuitions reflect the properties of the specific structure we inhabit, rather than universal features of existence. This view treats mathematics as ontologically primary, physical properties reduced to relations within a structure. Time corresponds to ordering relations. Space corresponds to geometric relations. Matter corresponds to elements participating in interactions defined by equations. Conscious observers correspond to complex substructures capable of processing information and forming internal models. From this perspective, physical reality becomes a special case of mathematical existence. The success of physics supports this interpretation indirectly. Every time a physical phenomenon is explained, it is reduced to mathematical relationships. The history of physics shows a progression toward deeper abstraction rather than toward more concrete description. Electromagnetism reduced forces to fields. Quantum mechanics reduced particles to wave functions. Relativity reduced gravity to geometry. Each reduction removes intuitive substance while preserving predictive power. The mathematical universe hypothesis extends this trend to its logical endpoint. It removes the distinction between mathematical description and physical existence altogether. Reality consists of mathematical structures, and physical existence becomes a subset of mathematical existence. This proposal introduces new challenges. One challenge concerns why we observe simple laws rather than arbitrary complexity. The space of mathematical structures includes objects of immense complexity, many lacking regularity or symmetry. observed physical laws exhibit simplicity, locality, and stability. Explaining why observers find themselves in such structures requires additional reasoning. One approach invokes computability. Structures capable of supporting observers must permit stable, computable regularities. Uncomputable or highly irregular structures fail to support consistent information processing. This constraint restricts the subset of mathematical structures compatible with observation. Simplicity emerges not as preference, but as necessity for complexity to persist. Another challenge concerns probability. If all mathematical structures exist, assigning probabilities to observations becomes non-trivial. Counting structures requires a measure over an infinite space. Different measures produce different expectations. Resolving this issue parallels the measure problem encountered in cosmological multiverses, but extends it to a more abstract domain. Despite these difficulties, the mathematical universe hypothesis offers a unified perspective. It treats physical law, quantum branching, cosmological variation, and mathematical abstraction within a single framework. Multiverses arise not from ad hoc additions, but from taking successful theories at face value and extending them consistently. Within this framework, physical reality corresponds to one realized mathematical structure among many. The laws we observe reflect the internal relations of that structure. Constants reflect parameters defining that structure. Observers reflect substructures capable of self-reference and information processing. This view eliminates the need for an external generator of universes. No mechanism selects which universes exist. Existence follows from consistency. Selection enters only at the level of observation, as observers find themselves embedded within structures capable of sustaining them. The question of whether physical reality is just one mathematical structure becomes a question about ontology rather than physics alone. Physics provides the evidence that mathematical structures capture reality with increasing completeness. Philosophy addresses whether this capture constitutes identity. Within the mathematical universe framework, the distinction dissolves. Physical reality does not sit on top of mathematics. It is mathematics, experienced from the inside by structures capable of observation. Our universe becomes one solution among many, not privileged by existence, but distinguished by internal properties that permit complexity, stability, and awareness. This perspective extends the multiverse beyond space, time, and quantum branching into the domain of abstract structure. It frames existence itself as mathematical, with physical experience arising from particular relational patterns rather than from a fundamentally non-mathematical substrate. Understanding how prediction, probability, and explanation operate within this framework remains an open problem. The hypothesis pushes the limits of what counts as scientific explanation by grounding existence itself in abstract consistency rather than dynamical origin. Within the broader arc of multiverse ideas, mathematical universes represent the most extreme endpoint. They replace physical generation with logical existence and treat reality as a member of an infinite set defined by mathematics alone. From that vantage point, the universe we observe becomes one internally consistent structure among many, characterized not by uniqueness, but by the particular relations that define it. Cosmological theories that allow multiple universes also raise a concrete physical question concerning observation. If our universe formed as a localized region within a larger inflating spacetime, then interactions between neighboring regions may have occurred during its earliest moments. These interactions, if they happened, would not resemble collisions between objects moving through space. They would involve the interaction of expanding spacetime regions governed by relativistic field dynamics. Any observable consequences would be subtle, indirect, and confined to the oldest accessible signals in the universe. In models of eternal inflation, individual universes form as bubbles that nucleate within an inflating background. Each bubble represents a region where inflation ends locally and reheating begins. As the bubble expands, its interior evolves according to standard cosmological processes. Other bubbles may nucleate nearby in the inflating background, and in some circumstances, their expanding boundaries intersect. When such intersections occur, the interaction takes place at relativistic speeds and involves the collision of field configurations rather than material objects. Theoretical work on bubble collisions treats these events using relativistic field theory coupled to general relativity. The boundaries of bubbles correspond to regions where scalar fields transition between different vacuum states. When two such boundaries intersect, the fields interact, producing disturbances that propagate inward from the collision region. These disturbances alter local conditions within the affected region of spacetime. The challenge lies in determining whether any such alteration could persist long enough and with sufficient coherence to leave an observable imprint. Any observable signal from a bubble collision must satisfy several constraints. The signal must survive cosmic expansion, avoid being erased by subsequent physical processes, and fall within the portion of the universe that remains observable today. The earliest epoch accessible to observation is encoded in the cosmic microwave background, which preserves information from the time when the universe became transparent to radiation. As a result, most proposed observational signatures focus on subtle features imprinted on this background radiation. The cosmic microwave background represents a nearly uniform bath of radiation with small temperature variations across the sky. These variations encode information about density fluctuations present in the early universe. Precision measurements reveal a statistically well-defined pattern consistent with inflationary predictions. Any additional signal from a bubble collision would need to appear as a deviation from this expected statistical structure. One proposed signature involves localized temperature anisotropies with specific geometric properties. A collision could produce a circular or disk-like region on the sky with slightly different temperature or polarization properties compared to the surrounding background. The size, contrast, and statistical profile of such a region would depend on the energy scale of inflation, the properties of the colliding vacua, and the relative timing of the collision with respect to our observable horizon. Theoretical models predict a range of possible effects, rather than a single distinctive pattern. Some collisions produce sharp boundaries between regions with different temperature statistics. Others generate smoother gradients or subtle distortions in polarization patterns. In all cases, the predicted signals remain small compared to the overall amplitude of primordial fluctuations generated by inflation itself. Searches for such signatures rely on high-precision maps of the cosmic microwave background. Satellite missions such as Wilkinson, Microwave Anisotropy Probe and Planck Satellite have produced full-sky maps with unprecedented sensitivity. These datasets allow detailed statistical tests of isotropy, Gaussianity, and angular correlations across the sky. Analyses of these datasets have identified a small number of anomalies. These include large-scale power asymmetries, unusually cold or hot regions, and alignments of low-order multipoles. Such features attract attention because they deviate slightly from the simplest inflationary predictions. Interpreting them requires caution, as statistical anomalies naturally arise in any finite dataset drawn from a random process. One frequently discussed feature is a large, relatively cold region of the microwave background. Some studies have explored whether such a region could result from a bubble collision occurring early in cosmic history. Models can be constructed in which a collision produces a localized suppression of temperature fluctuations consistent with certain observed features. At the same time, alternative explanations exist within standard cosmology, including the presence of large-scale structures along the line of sight or statistical variation within Gaussian fluctuations. Polarization provides an additional observational handle. The polarization of the cosmic microwave background encodes information about the velocity and density of matter at the time of last scattering. Bubble collisions may produce distinctive polarization patterns correlating correlated with temperature anomalies. Detecting such correlations requires extremely precise measurements, as polarization signals are weaker than temperature fluctuations and more susceptible to foreground contamination. Foregrounds present a persistent challenge. Emission from dust, gas, and synchrotron radiation within our own galaxy contaminates microwave observations. Separating primordial signals from foreground contributions requires careful modeling and multi-frequency analysis. Small residual errors can mimic or obscure subtle effects attributed to exotic early universe phenomena. Instrumental limitations also constrain what can be detected. Finite angular resolution limits sensitivity to small-scale features. Detector noise introduces uncertainty. Systematic effects related to calibration, scanning strategy, and data processing can imprint patterns that resemble cosmological signals. Extensive cross-checks and independent analyses are required to assess the robustness of any claimed anomaly. Beyond the cosmic microwave background, other observational channels have been considered. Large-scale structure surveys map the distribution of galaxies across cosmic time. A sufficiently strong early disturbance could, in principle, alter matter distribution on large scales. Gravitational waves generated during bubble collisions provide another potential signal, as collisions involve violent field dynamics capable of producing space-time perturbations. Gravitational wave backgrounds from bubble collisions would occupy frequency ranges determined by the energy scale of inflation and the dynamics of the collision. Current gravitational wave detectors focus on much lower energy phenomena, such as compact object mergers. Proposed future detectors may probe higher frequency backgrounds, but isolating a signal associated uniquely with bubble collisions remains challenging. A central difficulty lies in degeneracy. Many early universe processes produce similar observational signatures. Inflationary features, phase transitions, topological defects, and astrophysical foregrounds can all generate patterns that overlap with those predicted for bubble collisions. Distinguishing among these possibilities requires detailed modeling and statistical discrimination rather than direct identification. Another difficulty arises from cosmic variance. Observations of the largest angular scales rely on a single realization of the universe. Statistical uncertainties remain irreducible at those scales because only one sky exists to observe. This limits confidence in interpreting large-scale anomalies as evidence for rare events rather than chance fluctuations. Theoretical uncertainty compounds these observational challenges. Models of eternal inflation and bubble collisions involve parameters that remain poorly constrained, including the shape of inflationary potentials and the distribution of vacuum states. Different assumptions lead to different predictions for collision frequency, strength, and observational appearance. Without a well-defined probability distribution over these parameters, translating non-detections into strong constraints remains difficult. As a result, current searches focus on consistency rather than confirmation. Observational data can rule out classes of models that predict large, frequent, or strongly disruptive collisions. The absence of dramatic signatures already constrains certain regions of parameter space. More subtle models remain compatible with existing data, neither confirmed nor excluded. The possibility that evidence may always remain indirect follows naturally from these constraints. Bubble collisions, if they occur, take place near or beyond the limits of our observable horizon. Signals weaken as they propagate inward and compete with dominant inflationary fluctuations. Observational access remains limited to relic radiation and large-scale statistical patterns rather than direct causal traces. Indirect evidence plays a familiar role in cosmology. Dark matter, dark energy, and inflation itself remain inferred from gravitational and statistical effects rather than direct detection. In this context, indirect evidence does not imply speculative excess. It reflects the fact that early universe physics operates at energies and scales far removed from laboratory access. The distinction between prediction and retrodiction becomes important. Models of bubble collisions generate expectations for what might be seen given certain assumptions. Observations then constrain those assumptions. This process gradually narrows theoretical possibilities without producing decisive confirmation of specific, exotic events. Some researchers emphasize that the absence of clear observational signatures does not undermine the multiverse framework. Eternal inflation and vacuum structure arise from attempts to construct consistent theories rather than from observational motivation alone. Observations test consequences of these theories where possible, while accepting that some aspects may remain beyond empirical reach. Others emphasize caution. Theories that predict effects forever beyond observation challenge traditional criteria of scientific testability. The debate concerns whether indirect consistency with known physics suffices, or whether stronger observational engagement remains necessary for acceptance. Within current cosmology, the search for imprints of bubble collisions continues as a constrained technical effort. It relies on precision measurement, statistical rigor, and careful modeling rather than dramatic discovery. Any claimed signal must survive comparison against simpler explanations rooted in well-established physics. The cosmic microwave background remains the primary observational archive of the earliest accessible universe. Its structure encodes information about inflation, quantum fluctuations, and the initial conditions of cosmic expansion. Whether it also encodes traces of interactions with other universes remains an open, empirical question constrained by data quality, theoretical uncertainty, and fundamental limits of observation. As observational capabilities improve incrementally, constraints tighten, parameter space shrinks, models adapt. The absence of decisive evidence does not halt theoretical development, but it shapes which versions remain viable. The interplay between theory and observation continues without resolving the underlying question of multiplicity. Within this framework, bubble collisions remain a possibility grounded in theory and constrained by observation. Their detectability depends on dynamics that may or may not have occurred within our observable past. Evidence, if present, manifests statistically rather than unmistakably, embedded within signals shaped primarily by inflation and cosmic expansion. The effort to identify such evidence illustrates how cosmology operates at the boundary of what can be known. It combines precise measurement with theoretical inference while acknowledging limits imposed by causality and cosmic history. Modern physics relies on probability as a practical and conceptual tool. Probabilities appear in quantum mechanics as intrinsic features of measurement outcomes, in statistical mechanics as descriptions of large ensembles, and in cosmology as a way to relate theory to observation under uncertainty. In each of these domains, probabilities function because the underlying system admits a well-defined way to count possibilities or weight outcomes. When cosmological models introduce infinite numbers of universes or regions, this foundation becomes unstable. In an infinite universe or multiverse, every allowed event occurs infinitely many times. Every configuration compatible with the laws of physics appears not once, but endlessly. In such a setting, simple frequency-based reasoning loses meaning. The ratio of occurrences between two events becomes ill-defined when both numerator and denominator diverge. Statements such as event A is more likely than event B no longer follow automatically from counting. This difficulty arises immediately in eternal inflation. Eternal inflation predicts that inflating space grows without bound, continually producing new regions where inflation ends and standard cosmological evolution begins. The number of such regions increases without limit over time. If one attempts to count how many universes possess a particular property, the answer becomes infinite for nearly all properties that occur at all. Probability therefore cannot be defined by naive counting. To make predictions, one must introduce a prescription for comparing infinities. This prescription specifies how to regulate the infinite ensemble in a way that yields finite ratios. In cosmology, such a prescription is known as a measure. The measure assigns weights to different regions or histories, allowing probabilities to be defined as relative frequencies within a regulated subset. The measure problem refers to the ambiguity inherent in choosing this prescription. Different measures correspond to different ways of slicing spacetime, ordering events, or limiting the region under consideration. Because eternal inflation produces an unbounded spacetime volume, any cutoff introduced to regulate infinity depends on how it is implemented. Changing the cutoff procedure often changes the resulting probabilities. This dependence creates a serious challenge. A physical prediction should not depend sensitively on arbitrary choices made by the theorist. In many multiverse models, however, predicted probabilities for observable quantities vary dramatically depending on the chosen measure. The same underlying theory can yield incompatible predictions when paired with different regulation schemes. Several classes of measures have been proposed. One approach introduces a global time cutoff. In this scheme, one counts events that occur before a chosen time and takes the limit as that time goes to infinity. Different choices of time coordinate lead to different results. Proper time cutoffs, scale factor cutoffs, and light cone time cutoffs all regulate infinity in distinct ways, producing different probability assignments. Another approach focuses on local measures. Instead of counting events across the entire inflating spacetime, local measures restrict attention to a single world line or causal patch. Probabilities are defined by the experiences encountered along that world line. This avoids some global infinities, but introduces dependence on the choice of observer and initial conditions. Both approaches face difficulties. Global measures struggle with paradoxes related to exponential expansion, such as youngness problems, where most observers appear at extremely early times. Local measures struggle with dependence on initial conditions and with excluding large portions of the multiverse that may be physically relevant. The measure problem becomes especially acute when combined with anthropic reasoning. Anthropic arguments rely on conditioning probabilities on the existence of observers. To apply such conditioning, one must know how frequently different observer-containing regions occur. Without a well-defined measure, anthropic predictions remain ambiguous. Different measures yield different expectations for observed constants, such as the cosmological constant. This ambiguity affects predictability. In standard physics, a theory gains credibility by making robust predictions that can be tested against observation. In multiverse frameworks with unresolved measure problems, predictions often become conditional and measure-dependent. Agreement with observation may reflect flexibility rather than explanatory power. This situation raises a deeper question about the role of prediction in science. Scientific theories have historically balanced explanation and prediction. Some theories explain known phenomena within a broader framework before making novel predictions. Others predict new effects that later receive experimental confirmation. In both cases, predictability functions as a constraint on theory building. Multiverse models strain this balance. When a theory allows a wide range of outcomes and relies on selection effects to explain observed values, prediction shifts from determining specific outcomes to determining probability distributions. Observations then test whether observed values are typical or atypical within those distributions. Typicality becomes central. A theory must specify whether the observed universe represents a typical realization among those compatible with observation. Without a clear measure, typicality cannot be assessed reliably. This undermines the ability to judge whether a theory successfully accounts for what is observed or merely accommodates it. Attempts to regulate infinity aim to restore predictability. One strategy involves identifying physically motivated cutoffs rather than arbitrary ones. For example, cutoffs based on causal structure, such as restricting attention to regions within a causal diamond, attempt to ground the measure in spacetime geometry rather than coordinate choice. Another strategy seeks dynamical selection. In some models, certain vacua dominate the volume distribution due to their stability or transition rates. If such dominance emerges robustly across different measures, predictions may become less sensitive to regulation details. Research in this area explores whether late-time attractors exist in the space of solutions. Quantum cosmology offers another angle. Some approaches attempt to derive probabilities from a fundamental quantum state of the universe, using path integrals or wave functions defined over space-time geometries. In these approaches, probabilities arise from amplitudes rather than from counting universes. Translating these amplitudes into observational probabilities remains challenging, especially in the presence of infinite configuration spaces. Despite these efforts, no consensus has emerged. Different regulation schemes continue to produce different answers. Some resolve particular paradoxes while introducing new ones. The absence of a unique, compelling measure reflects the novelty of the problem rather than a simple technical gap. The breakdown of probability in infinite settings has precedents outside cosmology. In mathematics, probability theory requires a well-defined measure space. Without such a structure, probabilities remain undefined. In cosmology, the physical system itself generates infinities, forcing the theory to supply its own measure rather than borrowing one from finite ensembles. This requirement pushes cosmology toward foundational questions. Defining probability becomes inseparable from defining what counts as an event, an observer, or a universe. These definitions depend on physical assumptions about space-time, quantum mechanics, and observation. The measure problem therefore sits at the intersection of physics, mathematics, and philosophy. Science can function under uncertainty, but it requires constraints. In multiverse frameworks, constraints arise from internal consistency, compatibility with known physics, and the requirement that predictions remain stable under reasonable variations of assumptions. Measures that produce wildly unstable or paradoxical predictions lose credibility even without direct observational refutation. Predictability in this context becomes comparative rather than absolute. Instead of asking whether a theory predicts a unique outcome, one asks whether it predicts a narrow range of outcomes compared to alternatives. Theories that concentrate probability around observed values gain plausibility. Theories that spread probability broadly across incompatible outcomes lose explanatory power. Attempts to regulate infinity therefore aim to recover this comparative predictability. By narrowing distributions, stabilizing typicality, and reducing dependence on arbitrary choices, a successful measure would allow multiverse theories to make meaningful contact with observation. The search for such a measure remains ongoing. The measure problem does not imply that multiverse theories are unscientific. It reflects the difficulty of extending probabilistic reasoning into regimes where traditional assumptions fail. Similar difficulties appeared historically when probability entered physics through statistical mechanics and quantum theory. Resolution required new conceptual frameworks rather than abandonment of probability altogether. In cosmology, that resolution has yet to fully emerge. Theories of inflation, vacuum structure, and quantum mechanics provide strong internal motivation for considering infinite ensembles. Making sense of probability within those ensembles remains a foundational task. Progress depends on clarifying how infinities arise, how they can be regulated, and how predictions can remain meaningful in their presence. The challenge of probability in infinite universes therefore marks a frontier rather than a dead end. It signals that existing conceptual tools require extension to handle the scale and scope introduced by modern cosmological theory. Scientific theories operate within a methodological framework shaped by centuries of practice. That framework rests on a small number of principles that guide how explanations are constructed, how claims are evaluated, and how knowledge advances. Among these principles are internal consistency, empirical adequacy, and the ability to connect abstract models to observation. When new theories emerge that strain these principles, the tension does not immediately signal failure. It signals a boundary where established methods encounter new domains. A theory counts as scientific when it offers a coherent mathematical or conceptual structure that connects assumptions to observable consequences. The structure must be precise enough to generate expectations about phenomena, and those expectations must be constrained by the theory rather than adjusted freely to fit data. Predictive power does not require that every outcome be uniquely determined, but it does require that the space of possible outcomes be limited in a way that allows comparison with observation. Testability plays a central role in this framework. A testable theory exposes itself to potential conflict with data by making claims that could, in principle, be shown false. These claims may involve direct predictions, statistical distributions, or correlations between measurable quantities. Theories differ in how directly they confront experiment, but they share a commitment to being shaped by empirical feedback rather than insulated from it. Falsifiability enters as a practical criterion rather than an absolute rule. In its simplest form, falsifiability requires that a theory exclude some possible observations. A theory that accommodates every conceivable outcome without restriction fails to guide inquiry. In practice, however, many successful theories resist simple falsification. They operate within networks of auxiliary assumptions, approximations, and idealizations that complicate the relationship between theory and data. Cosmology has long occupied an unusual position with respect to these criteria. Unlike laboratory sciences, it studies a single object observed from a single location at a single moment in its history. Experiments cannot be repeated under controlled conditions. Instead, cosmology relies on observation of relic signals, statistical inference, and consistency across independent lines of evidence. These constraints shape what testability means in a cosmic context. The multiverse enters this methodological landscape as a consequence of theories developed for other reasons. Eternal inflation arises from attempts to explain the smoothness and flatness of the universe. Vacuum landscapes arise from attempts to unify gravity with quantum mechanics. Quantum branching arises from attempts to interpret the formalism of quantum mechanics without modification. In each case, multiplicity appears as a byproduct of extending existing theories rather than as an independently proposed hypothesis. This origin matters for how multiverse ideas relate to scientific method. Multiverse models are rarely proposed as standalone explanations. They emerge from theoretical frameworks already constrained by empirical success in accessible regimes. Inflation accounts for the cosmic microwave background and large-scale structure. Quantum mechanics accounts for laboratory experiments with extraordinary precision. String-inspired models incorporate known principles of quantum field theory and gravity. The multiverse inherits credibility from these parent theories while extending them into less accessible domains. The challenge arises when extension outpaces observation. Multiverse models often make claims about regions or branches that remain causally disconnected from us. Direct observation of those regions lies outside current and possibly future technological capability. This raises the question of whether a theory that refers to unobservable entities can remain scientific. Science has encountered similar situations before. Atoms were inferred long before they could be directly observed. Neutrinos were postulated to preserve conservation laws before detection became possible. Black holes were predicted as solutions to Einstein's equations decades before observational confirmation. In each case, unobservable entities gained acceptance because they played indispensable roles in theories that made testable predictions elsewhere. The multiverse differs in degree rather than in kind. Its components may remain permanently unobservable, yet the theories that imply them continue to make testable predictions within our observable universe. Inflation predicts specific statistical properties of primordial fluctuations. Quantum mechanics predicts interference patterns and energy spectra. High-energy theories constrain particle interactions and symmetries. The multiverse does not replace these predictions, it accompanies them. Falsifiability becomes more subtle under these conditions. A multiverse framework does not typically predict a single outcome. it predicts a distribution of possible outcomes across an ensemble. Testing such a framework involves assessing whether observed values fall within the predicted distribution and whether alternative theories produce narrower or incompatible distributions. Failure occurs not when a single observation contradicts the framework, but when observed patterns consistently fall outside its allowed range. This mode of testing resembles statistical inference rather than direct falsification. Theories are evaluated based on how well they concentrate probability around observed values compared to competitors. A theory that spreads probability broadly across incompatible outcomes loses explanatory power, even if it technically allows what is observed. This comparative approach already operates in areas such as cosmological parameter estimation and model selection. The concern arises when probability distributions themselves depend on unresolved choices. In multiverse cosmology, measures used to define probabilities across infinite ensembles remain ambiguous. Different measures produce different distributions, weakening predictive sharpness. This ambiguity challenges the traditional role of prediction as a discriminator between theories. The response to this challenge divides along methodological lines. One view treats unresolved measure problems as temporary technical obstacles. From this perspective, multiverse theories remain scientific because they arise from testable frameworks and may become predictive once foundational issues are resolved. Research continues toward identifying physically motivated measures that stabilize predictions. Another view treats measure dependence as a structural flaw. From this perspective, a theory that cannot generate stable predictions even in principle fails to meet scientific standards. The multiverse then appears closer to metaphysical speculation than to empirical science, regardless of its mathematical consistency. The boundary between physics and metaphysics has never been static. Concepts once regarded as metaphysical often enter physics when they become mathematically precise and empirically constrained. Space, time, causality, and even probability itself underwent such transitions. The question is not whether a concept is metaphysical in origin, but whether it becomes operationally integrated into a framework that constrains observation. Cosmology has repeatedly stretched scientific norms to accommodate its subject matter. The Big Bang model inferred a cosmic beginning long before direct evidence existed. Inflation proposed dynamics at energy scales far beyond experimental reach. Dark matter and dark energy remain unidentified at the particle level, yet their gravitational effects structure cosmological models. Each extension required accepting indirect evidence as sufficient when direct access proved impossible. These precedents do not guarantee acceptance of multiverse ideas, but they contextualize the debate. Science adapts its methods when confronting new scales and regimes, provided that adaptation preserves internal discipline. The risk lies not in extending explanatory scope, but in losing constraint. Multiverse frameworks remain anchored to scientific method to the extent that they remain constrained by their parent theories. Eternal inflation remains tied to inflationary dynamics. Landscape models remain tied to consistency requirements of quantum gravity. Quantum branching remains tied to the formalism of quantum mechanics. Abandoning these anchors would move the multiverse beyond physics, but retaining them keeps it within a broadened methodological boundary. The role of observation shifts under this expansion. Instead of confirming the existence of other universes directly, observation constrains the space of viable theories that imply them. Absence of certain signatures rules out classes of inflationary models. Observed parameter values constrain allowed regions of the landscape. Laboratory tests constrain interpretations of quantum mechanics. Indirect pressure accumulates even without direct detection. Predictability survives in altered form. It becomes probabilistic, conditional, and comparative rather than absolute. Theories compete based on how tightly they link underlying principles to observed regularities. Multiverse models that fail to narrow expectations lose ground to those that succeed, regardless of whether other universes remain unseen. The scientific method does not require certainty about every aspect of a theory's ontology. It requires disciplined reasoning, internal coherence, and accountability to observation wherever observation applies. Multiverse ideas challenge these requirements by operating near their limits, but they do not automatically violate them. Whether multiverse concepts ultimately belong to physics depends on their future development. If they remain mathematically consistent but observationally unconstrained, they risk drifting into metaphysics. If they integrate probability, selection, and dynamics into stable predictive frameworks, they remain within science even without direct verification. Cosmology has repeatedly expanded the scope of scientific explanation by confronting regimes inaccessible to experiment. The multiverse represents another such expansion. Its status reflects not a departure from scientific method, but a stress test of how far that method can stretch while remaining grounded in evidence and constraint. The introduction of multiverse frameworks alters how existence is situated within physical theory. Instead of describing a single, all-encompassing universe governed by uniquely fixed laws, these frameworks describe a broader structure in which many regions, histories, or solutions coexist. Within such a structure, familiar concepts such as rarity, inevitability, and uniqueness acquire different meanings, not through philosophical assertion, but through changes in how physical explanation is organized. In a single universe framework, existence carries an implicit sense of necessity. The laws of physics appear as the only possible laws, and the resulting universe appears as the only possible outcome. Under this view, the existence of galaxies, stars, planets, and observers follows from those laws alone. Questions about rarity arise mainly in local contexts, such as how common Earth-like planets may be within a galaxy, or how frequently life might emerge under given conditions. Multiverse frameworks shift this context. When physical laws or initial conditions vary across different regions, existence becomes conditional rather than necessary. A universe like ours appears as one realization among many, permitted by deeper laws. Rarity then refers not to whether something exists at all, but to how frequently it occurs across the ensemble of possibilities. A phenomenon can be rare without being improbable in the sense of violating physical law. Within this framework, the question of whether we are rare or inevitable depends on which level of description is adopted. At the level of fundamental laws, the processes that generate universes may operate generically, producing a wide range of outcomes without targeting any specific one. At the level of local conditions, the emergence of complex structures may require a narrow alignment of parameters. A universe like ours may therefore be rare within the full ensemble, while still arising inevitably somewhere if the ensemble is sufficiently large. This distinction alters how necessity is understood. Necessity no longer applies to individual outcomes, but to the existence of the ensemble itself, given the underlying dynamics. If inflation or quantum branching operates continuously, then the production of diverse outcomes follows automatically. Under such conditions, the question shifts from why this universe exists to why observers find themselves in this type of universe rather than another. Selection effects enter naturally at this stage. Observers require stable matter, long-lived energy sources, and sufficient time for complexity to develop. These requirements restrict observation to a subset of all possible universes. Observed conditions therefore reflect compatibility with observation rather than representativeness of the full ensemble. This restriction does not imply design or purpose. It reflects the physical constraints imposed by the existence of observers as physical systems. Concerns about uniqueness often arise from this shift. In a multiverse context, uniqueness ceases to be a defining feature of existence. The Earth may not be the only planet. The Milky Way may not be the only galaxy. Our universe may not be the only universe. Each step extends a pattern already present in scientific history. Loss of uniqueness at one level does not eliminate structure or meaning at another. Significance within physical theory does not derive from exclusivity, it derives from relational structure and causal coherence. A star remains significant as a physical system because of the processes it hosts. Regardless of how many stars exist elsewhere, a life-bearing planet remains significant because of the complexity it supports, not because it is singular. The presence of many similar systems does not diminish the properties of any one system. The multiverse reframes significance in a similar way. Our universe remains the context in which all accessible physical processes occur. All observation, experiment, and experience remain confined to this region. The existence of other universes does not alter the internal structure of ours. Physical laws, histories, and causal relations retain their full explanatory power locally. Questions about whether the multiverse diminishes meaning often arise from conflating uniqueness with value. In physical terms, value does not enter as a parameter. Physics describes what exists and how it behaves. Meaning, in the sense relevant to human experience, arises from cognitive and social processes embedded within physical systems. These processes remain unaffected by the number of universes permitted by theory. Within a multiverse, human existence occupies a specific physical context shaped by local conditions. Biological evolution, cultural development, and individual experience unfold within this context according to well-understood mechanisms. The presence of other universes does not interfere with these processes. Human concerns, goals, and relationships remain grounded in local interactions rather than global ontology. The perception of diminished significance often reflects a mismatch between intuitive expectations and abstract description. Intuition evolved to operate within small-scale environments where singularity and centrality carried practical meaning. Cosmological theory operates at scales far removed from such environments. Adjusting intuition to accommodate this mismatch requires conceptual rather than empirical change. Historical precedents illustrate this adjustment. The displacement of Earth from the center of the cosmos altered humanity's spatial self-conception. The recognition that the Milky Way is one galaxy among many altered cosmic scale. Each shift initially provoked discomfort, followed by integration into a broader understanding. The multiverse represents a further extension along the same trajectory. Within this broader context, human perspective remains necessarily local. Observation occurs from within one universe, within one galaxy, within one planetary environment. No cognitive or experimental process grants access to the full ensemble. Perspective remains bounded by causality and information flow. This boundedness shapes how meaning is constructed and experienced. Existence, as encountered by observers, remains singular in practice. Each observer occupies one branch, one region, one history. Alternative possibilities exist only as theoretical inferences rather than experiential realities. This asymmetry preserves the structure of lived experience even within frameworks that permit multiplicity at a deeper level. Psychological responses to cosmic plurality vary. Some individuals experience reduced attachment to anthropocentric narratives. Others experience increased appreciation for local complexity and fragility. These responses reflect differences in how abstract knowledge integrates with emotional and social cognition rather than consequences of physical theory itself. From a scientific perspective, psychological impact does not determine validity. Theories succeed or fail based on explanatory coherence and empirical constraint. Human responses remain secondary, though they influence how theories are communicated, taught, and culturally assimilated. Cosmic plurality also alters how contingency is understood. Events that appear extraordinarily unlikely within a single universe framework become expected somewhere within a sufficiently large ensemble. This reframes improbability as a statement about frequency rather than impossibility. Local histories remain contingent even if global structure renders them inevitable somewhere. Within this view, existence combines contingency and inevitability without contradiction. Any particular outcome may be contingent, dependent on local conditions and chance. The existence of some outcome of that type becomes inevitable given the scale of the ensemble. This duality reflects how probability operates across large systems, rather than a failure of explanation. Meaning does not disappear under this duality, it becomes contextual. Meaning attaches to processes, relationships, and experiences within a given history. The existence of other histories does not negate the structure of this one. Causal chains remain intact. Responsibility, agency, and understanding remain grounded in local dynamics. The multiverse therefore alters metaphysical background assumptions without dissolving practical reality. It expands the scope of what physics considers possible while leaving the content of lived experience unchanged. Significance continues to arise from organization and interaction rather than from cosmic exclusivity. Within this framework, existence appears neither uniquely privileged nor trivial. It appears as one realized configuration among many, distinguished by its internal structure rather than by its isolation. Observers emerge where conditions permit them. Understanding emerges where observers develop models of their environment. Both remain physically grounded phenomena. The psychological impact of cosmic plurality depends on how these ideas are interpreted rather than on their physical content. When framed as displacement, plurality can feel diminishing. When framed as context, it situates human existence within a broader, law-governed structure without erasing its local richness. From the standpoint of cosmology, these implications follow from extending successful theories rather than from redefining human value. Physics describes how many universes may exist. It does not assign importance. Importance remains an emergent property of complex systems interacting within specific environments. The multiverse thus reshapes the conceptual backdrop against which existence is understood, while leaving the mechanisms that generate experience untouched. It challenges assumptions about uniqueness without undermining the coherence of local reality. Within that local reality, meaning continues to arise through physical processes that remain fully operative regardless of how many other universes theory permits. Modern cosmology operates at the intersection of direct observation, theoretical inference, and extrapolation beyond accessible evidence. This intersection defines a boundary that remains implicit in much of scientific practice, but becomes especially visible when discussing multiverse frameworks. On one side lie phenomena constrained by measurement, repeatable observation, and tightly tested theory. On the other side lie consequences inferred from extending those theories into regimes that cannot currently be observed and may never be directly accessible. What we truly know rests on a limited but robust foundation. Observations constrain the age, expansion history, and large-scale structure of the observable universe. Measurements of the cosmic microwave background, galaxy distributions, and gravitational dynamics support a coherent cosmological model governed by general relativity, quantum field theory, and well-characterized initial conditions. These elements form the empirical core of modern cosmology. From this core, inference extends outward. Inflation is inferred from patterns in primordial fluctuations rather than observed directly. Dark matter and dark energy are inferred from gravitational effects rather than identified as particles or fields in laboratory experiments. Each inference rests on consistency across independent observations rather than on direct detection. The multiverse enters at a further step along this inferential chain. Multiverse frameworks arise when well-supported theories are applied beyond the domain of current observation. Eternal inflation follows from specific inflationary dynamics. Vacuum multiplicity follows from attempts to unify gravity with quantum mechanics. Quantum branching follows from interpreting the mathematical formalism of quantum mechanics without modification. None of these ideas originate as explanations for unexplained data. They emerge as consequences of extending theories already constrained by observation. This mode of reasoning preserves internal consistency but weakens empirical closure when consequences lie beyond causal contact. Confirmation and refutation operate indirectly. Theories are evaluated by how well they account for what is observed locally, how coherently they integrate known physics, and how stable their predictions remain under variation of assumptions. The boundary between knowledge and speculation appears where empirical leverage diminishes. The multiverse persists within this boundary because it occupies a structurally stable position in theoretical physics. Removing it often requires altering or constraining theories in ways that conflict with their success elsewhere. Eliminating eternal inflation demands modifying inflationary dynamics. Eliminating vacuum multiplicity demands restricting solutions to quantum gravity. Eliminating quantum branching demands modifying the formalism of quantum mechanics. Each alternative introduces its own conceptual or empirical costs. Persistence does not imply certainty. It reflects resilience under theoretical pressure. Multiverse ideas remain present because they solve internal tensions within theories more effectively than available alternatives. They remain uncertain because their distinguishing consequences lie near or beyond observational limits. Future progress may shift this boundary. Advances in observational cosmology continue to refine constraints on inflationary models, primordial fluctuations, and large-scale structure. Improved measurements may rule out classes of inflationary dynamics that strongly favor multiverse behavior. They may also identify features that narrow theoretical possibilities without confirming multiplicity directly. Advances in fundamental theory may alter the landscape as well. A deeper understanding of quantum gravity could reduce or reorganize the space of allowed solutions. New principles could constrain vacuum structure or eliminate entire classes of multiverse-generating dynamics. Conversely, such advances could strengthen the theoretical case for multiplicity by demonstrating that alternative frameworks fail under consistency requirements. Limits remain intrinsic. Causal horizons restrict access to regions beyond the observable universe. Quantum decoherence prevents communication between branches of the wave function. Cosmic variance limits statistical certainty on the largest scales. These limits arise from physical law rather than technological insufficiency. They define a ceiling on what cosmology can observe directly. Within these limits, inference remains the primary tool. Cosmology proceeds by constructing models that extend beyond observation while remaining anchored to it. The success of this approach depends on maintaining disciplined separation between what is measured, what is inferred, and what is hypothesized. Confusion arises when these categories blur. Living inside one universe shapes all observation. All data originate from within a single causal region. All experiments occur under local physical conditions. All theories are tested against phenomena accessible within this region. Other universes, if they exist, remain external to experience by construction. Their influence enters only through indirect effects encoded in local physics. This situation does not isolate cosmology from scientific practice. It aligns cosmology with other fields that infer unobservable entities from observable consequences. The difference lies in degree rather than principle. Multiverse theories push inference to its outer edge without abandoning methodological discipline. The quiet boundary between knowledge and speculation therefore functions as a working interface rather than a fixed line. It shifts as theory advances and observation improves. It marks where confidence transitions into conditional acceptance rather than where science ends. Within this framework, the multiverse occupies a provisional status. It remains neither established fact nor unfounded conjecture. It persists as a consequence of extending successful theories into regimes where direct evidence fades, but internal coherence remains strong. Living inside one bubble does not grant access to the rest. It does, however, permit understanding of the mechanisms that could produce such a structure. Cosmology describes the conditions under which universes may form, evolve, and remain isolated. It does so from within one realized history, using laws inferred from local observation. This constraint defines the character of cosmological knowledge. It remains local in data and global in implication. It balances empirical grounding with theoretical reach. The multiverse represents the furthest extension of this balance, where explanation remains mathematically precise while observation becomes indirect. At this boundary, cosmology continues to operate as a science of inference. It accepts limits imposed by causality and information while pursuing coherence across theory and data. Knowledge advances not by resolving every uncertainty, but by clarifying which uncertainties arise from ignorance and which arise from the structure of the universe itself. Within that distinction, the multiverse remains an open possibility shaped by what is known, constrained by what can be tested, and limited by what can be observed.